Hello everybody, my name is Vlado, and today I want to talk about some advantages and disadvantages of computing on FPGAs in the context of zero-knowledge proofs. So, basic motivation is that zero-knowledge proofs right now are slow and expensive. So, if we are talking about expensive, we can divide the costs into two categories. First of which is on-chain cost, and this only holds if we are talking about ZK proofs in regards of scaling blockchains. And here we already have some kind of solutions. By introducing blobs, we were successfully able to reduce the cost of L2 transaction, and the cost of verification can be successfully reduced by aggregating multiple proofs into the single one and amortize the cost of verification of these multiple proofs. With off-chain cost, we can divide this off-chain cost into also some kind of categories. We need to pay for the hardware, we need to pay for the energy, and we need to somehow manage this heavy hardware in order to accelerate the zero-knowledge proofs. And currently the trend is that the big projects are willing to pay a lot of money for heavy hardware in order to reduce the proving cost. However, from our point of view, it's not viable to the future, so our goal is to build cost-efficient prover without sacrificing the speed. Next, I want to talk about our FPGA journey, and in order to do so, I am using the MSM as the main bottleneck. Everybody surely know what MSM is, so I will just demonstrate our FPGA journey using MSM. This is the main bottleneck. It can take up to 80% of the computation of proof within ZK snarks. The best algorithmic way how to compute MSM is Pippenger algorithm. It guarantees us minimal number of group addition operations, and this Pippenger algorithm is split into three parts, where the most computation heavy part is bucket accumulation. You can notice that only bucket accumulation is dependent directly on the size of the instance of MSM, and this size of the instance, this big N, can be pretty huge in practice. We are talking about 2 to the power of 25 or 2 to the power of 26 for real-time use cases. The other two parts of the algorithm are only dependent on this C constant, and this C constant comes directly from the Pippenger algorithm, where Pippenger splits the big scalars inside the MSM into these chunks, and the bit width of one chunk is this C constant. In practice, we are talking about values like 15, 16, 17. The main point of the Pippenger algorithm is that each column of this bucket accumulation table can be processed fully independent and in parallel, and each column have its own bucket set, which is also completely independent. Now, what's the main goal of this heavy computation heavy part, this bucket accumulation part, is to sorting the input points into these buckets. So, as you can see in the example, the column, the cell value of our bucket accumulation table gives us the index of bucket, and we just add this point inside the bucket. And by adding points to the bucket, I mean we are performing elliptic curve addition operation. This is static operation where the inputs are fixed. There is no branching inside this operation, so it's like textbook example for fully pipelined architecture. With fully pipelined architecture, for those who are not familiar, we are just splitting this one operation into multiple stages, and each line in the slide represents the independent instance of our elliptic curve addition. So we are processing multiple elliptic curve additions in parallel, and with each clock cycle, once the pipeline is fully filled, we will get new results with every clock cycle. And this fully pipeline architecture is like tailor-made for implementation on FPGA, as we can achieve almost 100% resource utilization. To achieve this 100% utilization, we need to be able to fill this pipeline at all times. And in our design, the main point is this EC point adder, which is the yellow part in the image you can see. So it's like the biggest part of the whole design. So we need to be able to fill the pipeline at all the times of this EC adder. Problem where we are not able to fill, to achieve this 100% utilization is when there is a conflict in the input data. And by conflict in context of pipenger, I mean there can be a situation where we cannot use like input data directly inside the adder. So let's simulate our pipeline architecture. So at the first stage, we start by adding point 0 to the bucket 3. Next, stage 2, we are going to start adding point 1 to the bucket 10. And at the stage 3, there is a conflict. As I told, to finish the elliptic curve point addition, we need 100 stages. So the result of the first addition will be available after 100 stages. So the third line will get us the wrong result, as we are using the old value for bucket 3, not the new one. So there is a clear data race, and the result will be wrong. We need to postpone this bucket after these 100 stages, and we need to find 98 other non-conflicting additions in order to fully utilize our pipeline. And now, let's take a look what can be achieved with this pipeline architecture. So let's imagine this 100% utilization, which is not like achievable in practice, but we are very close. And let's imagine that one stage is 4 nanoseconds. It means that our FPGA will operate on 250 megahertz frequency. And if we take an example of MSM instance of size 2 to the power of 26, which is 1 billion EC additions, we can process these 1 billion EC additions in 4.3 seconds. The clear choice how to speed up this operation is to increase the frequency. However, then the memory will become the bottleneck. So we will not able to fill up the pipeline because the memory is too slow to keep up with the EC adder. So what's our solution is to use this multi-channel design, which we came up with. I won't go into the details, but the main idea of our multi-channel design is to process multiple columns of our bucket accumulation table at the same time. So with more data available, we can fill the adder easier and quicker than just with one channel design. As I said at the beginning, all the columns are independent, so there is no conflict between the columns itself. Also, the EC adder is completely independent component inside the design, so there is only one FIFO queue, which is filled by all the controllers. So the data is available for this EC adder to process instantly and faster than with one channel design. What are the main advantages? The first of all, we can reuse the same point multiple times. All the points are stored inside the main memory, inside the DDR memory, which is pretty slow. And with one channel design, we are going to use every point only once. With multi-channel design, we can use 1 point number of channel times. So that's the big advantage. And the second advantage is, as I said, each column is independent, so there is a quicker way how to fill the pipelines without collisions. Some results. With our multi-channel design, we are able to achieve up to 800 million EC additions per second. So we can clearly, easily utilize 2 EC adders at a frequency of 400 megahertz if we have enough resources inside the FPGA. So if we have big enough card to fit up 2 EC adders with this frequency, it is like possible to go up to 800 million EC additions per second. Again, if we translate this into our 2 to the power 26 MSM instance, we can process all the 1 billion EC additions in 1.3 seconds. And now, what is our takeaway from working with FPGA? I will compare the FPGA and GPU as only 2 possibilities of how to accelerate ZK proofs right now, because ASIC is still work in progress. So, from the development side of things, the cost of FPGA development is much higher than GPU development, as it is the direct consequence of the time we need to finish the FPGA end-to-end solution opposed to GPU, as with GPU it's basically software development plus some, you just need to write CUDA code, right? And with FPGA, just creating this image, building and testing and debugging, it can take you to tens of hours, just building process. Regarding the hardware price, also you can notice that FPGAs can be like almost 2 times more expensive than GPU cards. And what I want to emphasize is that the end-to-end proving is fast. So we did the benchmarks where we used GPU accelerated MSM and then this for end-to-end prover, and you can see the utilization in the image. There is a lot of idle states in end-to-end proving, and with GPU you can reuse the same device to accelerate also these parts by just calling different kernels. But with FPGA you need to buy like new hardware, implement the new algorithm, and somehow connect this to your end-to-end prover. So the cost of FPGA end-to-end prover can be much higher than the GPU prover. And also, what I want to point out is that in practice, even for MSM only, there are architectures that are using like multiple FPGAs for only MSMs. And here are my very rough estimates of the costs. What can we buy for more money? If it's justifiable, it's the question for you, if it's good enough to pay this kind of money for gaining not a lot of time. And what I want to also emphasize is that this is only MSM. So even if we get rid of completely of without MSM, we have end-to-end proving without MSM, we can achieve only 5 times speed up. If the MSM takes 80% of the computation. So our main takeaway is that end-to-end proving is hard, and we need more general hardware than just FPGAs, which can implement only the specific part of the algorithm. So we believe that the more general hardware is the right way to take right now. Also, the other thing is that we still don't know what prover is the clear choice, who will be the winner. And with more general hardware, you have to, you can like accommodate accordingly. So yeah, end-to-end proving is hard, and we are working on improving the other parts of end-to-end provers, as the MSMs and entities are not only bottlenecks right now.
Okay, thanks a lot. Yeah, we have time for one quick question.
Hi, thanks for an interesting presentation. I have a question about like typical use case for FPGAs, and if you've tried different kind of things. So I mean, these FPGAs today, or particularly what we see these days in the Zprize competition and so on. They're just pure FPGAs without having like additional, for example, ARM cores and so on. So what about, and we heard today like an interesting talk from Justin Drake about like having the foolproof essentially on a dedicated hardware. So what about like using the other type of FPGAs that have already like general purpose computation cores to perform, for example, the other tasks, to perform the front end from the prover, and then using the programmable part of FPGA really for the dedicated acceleration of critical functions. So that's one question. And another, you mentioned, I'm sorry for sticking two questions into one. Another one is that there is also like an argument for that FPGAs versus ASICs, they can be reprogrammed, and today's FPGAs can be reprogrammed very quickly in a ballpark of a couple of seconds. So if the workloads allow this, we can also have multiple functions. It's not, of course, as fast as having like multiple cores on GPUs, but you can actually reprogram. Have you maybe tried this, and like if you can comment also on this one? Thank you.
Yes, so I will start with the second question. We haven't tried to reprogram the FPGAs, but still, with if I compare FPGA to ASIC, the cost of ASIC will be much lower than FPGA. So these high-end FPGA cards can cost a lot. So that's the main reason why the FPGAs will not be used, I guess, in the long run. And regarding your first question, you asked about the FPGA with the ARM cores. Yeah. So there is still a question that you would need, like, again, high-end FPGA to be able to fit all the accelerated part to the FPGA and offload. As we can see right now, the problem is that the accelerated part, the MSM and entities takes like, they are pretty quick right now. So the heavy task is on CPU, so we need to somehow accelerate also those parts and not to offload them to the like bigger cards or something like that.
Okay, thanks a lot, everyone, and let's thank again Vladimir. If you